We all have those moments, right? Those sudden jolts where time kind of slows down.
Oh, yeah.
And you think, whoa, that was close. I could have died. Maybe a car swerving or, a misstep on a trail.
The near misses, they really stick with you, don't they? That instant fear, then just, wow, relief.
Absolutely. And the source for this deep dive shared a truly wild one from childhood falling from a third-floor doorway.
Third floor.
Yeah, where the balcony hadn't even been built yet,
Yeah.
landed on stones, apparently knocked out cold,
Oof.
and somehow woke up without a single scratch.
That's incredible. Just sheer luck. It forces you to think, doesn't it, about how fragile things are.
Totally. And it makes you wonder, like, in that specific instant, did they almost die?
Oh.
Or is there some sense in which they actually did die?
And that question, as out there as it sounds, is really our starting point today.
Right, because we're plunging into an idea the source describes as, well, complex, definitely mind-bending.
Yeah, the source said researching it felt like entering scientific hell, but they really tried to explain it simply.
So that's what we're trying to. The topic is quantum immortality.
Uh-huh.
And our mission is basically to unpack the core ideas from the source material, the weird physics, the thought experiments, all that stuff.
And different interpretations.
Exactly. To help you get a handle on what quantum immortality is even about. It's kind of a shortcut to understanding some really fundamental and, frankly, bizarre universal concepts.
And, well, to even start talking about quantum immortality, we first need to lay some groundwork. We have to talk about Schrödinger's cat.
Yes, the famous cat in the box. So walk us through that thought experiment, how the source lays it out.
Okay, so picture a sealed box.
Yeah.
Totally isolated. Inside, you've got a cat.
The poor cat.
Yeah. Along with a tiny bit of radioactive material, a Geiger counter aimed at it, a hammer connected to the counter, and a flask of poison right under the hammer.
Quite the setup. Sounds dangerous.
It's designed to be. The key is the radioactive decay. It's a pure quantum event, totally random. Let's say there's a 50-50 chance it decays in 1 hour.
Okay, 50-50. So if it does decay,
If an atom decays, the Geiger counter detects it. Click. It triggers the hammer falls, smashes the flask, releases the poison.
and the cat dies,
Right. But if the decay doesn't happen in that hour,
then nothing happens.
exactly, no click, hammer stays put, flask is fine, cat lives.
Simple cause and effect, it seems. But what's the quantum twist?
The twist is this. Until you actually open the box and look until you make an observation. The rules of quantum mechanics say that radioactive atom is in a superposition. It has both decayed and not decayed simultaneously.
Wait, both? How can it be both?
That's the weirdness. And because the atom state is linked to the cat's fate, the cat itself is considered to be in a superposition of states. It's, well, simultaneously alive and dead.
That just sounds impossible in our world. Like things are one way or the other.
Absolutely counterintuitive. And that was Erwin Schrödinger's point back in 1935 when he came up with this. It was a thought experiment to show how bizarre quantum theory seems when you scale it up to, cats.
Got it. And the source mentioned a little fun fact. The original German paper actually used the word Katze, which is a female cat.
That's right. Often gets translated as Inya in Russian, not the male uns. So technically, Schrödinger's female cat.
Yeah, okay. The source also used another analogy, right? Something more relatable, maybe.
Yeah, trying to grasp this different states at once idea. Imagine a friend who just disappeared years ago. Maybe they moved, changed completely, became a, I don't know, successful rapper somewhere else.
Okay.
To the people back home, in that old context, that friend is sort of dead to them, gone from that reality. But they're obviously very much alive and real elsewhere. Different realities depending on your viewpoint or interaction.
Right, that helps a bit. It hints at how something can exist differently depending on the context. Which leads us to thinking about different scales, different worlds, as the source puts it.
Exactly. The source breaks it down nicely. We've got our everyday macro world, cameras, people, houses, cars, things we interact with directly.
Then there's the mega world, planets, stars, galaxies. Really big stuff.
And both those worlds, the macro and the mega, they mostly follow predictable rules. Classical physics, Newton's laws, that kind of thing. Drop an apple, it falls.
Predictable.
Yeah.
But then there's the third world.
The micro world. Molecules, atoms, subatomic particles like electrons, photons. And down there, the source stresses classical physics just breaks down. It doesn't work.
Okay.
It's a realm where things happen that just don't make sense based on our everyday intuition. It's fundamentally weird.
That's where the rules get thrown out, isn't it?
Pretty much. And this is where that famous quote comes in, the one attributed to Richard Feynman that the source included.
Which one was that?
It's okay not to understand quantum mechanics because nobody understands it.
Huh. Well, that's reassuring, I guess.
A bit humbling, yeah. But we'll try to navigate it simply, like the source aimed to.
So one of the core weirdnesses, you mentioned it with the cat, is this idea of superposition.
Yes, exactly. At the quantum level, tiny objects like electrons or photons can exist in multiple possible states, multiple locations, multiple energy levels, whatever, all at the same time.
The source had an analogy for that too, didn't it? Like a book in a room.
Right. In our macro world, a book is either, lying flat on the table, or maybe it's standing up on the shelf. It's one or the other.
Makes sense.
But if it were a quantum book, superposition means it could be lying down and standing up, and maybe even rotating or hanging in the air, all simultaneously.
Which is just absurd for a book.
Utterly absurd for a book. But for microparticles, that's apparently their natural state of being. Multiple possibilities existing at once, until something interacts with them.
Okay, so that's something that interacts. That brings us to the next big hurdle, the observer effect, or the measurement problem.
Yes, this is absolutely central to all the quantum weirdness. It seems that we, or our instruments, our macro world, we don't like things being in superposition. We want to know, is it here or there? Is it spin up or spin down? We need a single answer.
So what happens when we try to, measure it, pin it down?
When you try to measure or observe a quantum object that's in superposition, the superposition collapses. It instantly snaps into just one of those possible states. That's the state you measure.
It just picks one. Why does looking at it or measuring it force it to choose?
Well, the source gives a really great analogy to explain why observation isn't passive at this scale. Think about billiard balls.
Okay, snooker table?
Right. Imagine you want to see where a billiard ball is going. You might shine a light on it, maybe take a photo with a flash. That flash sends out photons, light particles.
Uh-huh.
Those photons bounce off the relatively huge billiard ball and come back to your eye or camera. You see the ball. But the impact of those tiny photons on that big, heavy ball, it's negligible. It doesn't really change its path.
Right, it just keeps rolling.
But now, imagine your billiard ball is actually a single tiny photon itself.
Wow.
And you're trying to see it by hitting it with another photon from your flash.
Oh, so like two tiny things hitting each other.
Exactly. A photon hitting another photon is a major collision. It's like throwing a billiard ball at another billiard ball. The interaction drastically changes the path, the energy, the state of the photon you are trying to observe.
So you can't measure it without messing it up.
Precisely. The very act of trying to get information about the microobject fundamentally alters it. You don't see it as it was. You see it after your interaction has forced it into a single definite state.
Okay, that makes more sense. And the source was clear. Observation here doesn't mean like a person consciously looking. Right, it's not mind power.
No, not at all. That's a common misconception. Observation or measurement in quantum mechanics means any physical interaction where the tiny quantum system gets entangled with a larger macroscopic system like a detector, a screen, anything that can register its state.
So any device counts.
Any device, any interaction that's strong enough to leave a record, basically. Because that interaction inevitably disturbs the delicate quantum state. It's a physical consequence.
Got it. Physical, not magical. And the source mentioned the double slit experiment too, as another example.
Yeah, that's the classic demonstration. Electrons seem to act like waves going through both slits at once, unless you try to detect which slit they go through. Then suddenly, they act like particles and only go through one. The observation changes the behavior.
Wow. Okay. So superposition is real for tiny things, and measuring forces a single outcome. But why? Why does measuring do that? The source says scientists don't actually agree on one single reason, right? There are different interpretations.
That's right. There's no single universally accepted explanation for why the math of quantum mechanics works the way it does or what it implies about reality. There are different hypotheses, different interpretations.
And the source highlights two main ones.
Two big ones. First, there's the Copenhagen interpretation, developed back in the late 1920s, mostly by Niels Bohr and Werner Heisenberg.
The source couldn't resist the Breaking Bad nod there, could they?
Apparently not. Anyway, the core idea of the Copenhagen view is that, yes, quantum objects exist in superposition, and the act of measurement causes this superposition to collapse. One reality is randomly chosen, and all the other possibilities just cease to exist. Poof.
They just disappear.
Yeah.
Okay, that's one way to think about it. But that's not the one that leads to quantum immortality, is it?
No. For that, the source explains you need the other major interpretation, the many worlds interpretation, or MWI.
Many worlds. Sounds big.
It is, proposed by Hugh Everett III in 1957. And this is where things get really, really strange. Many worlds says that when a quantum measurement happens, or any quantum event with multiple outcomes,
Like the radioactive decay.
exactly, the universe doesn't just collapse to one outcome. Instead, the entire universe splits into multiple parallel branches, a separate universe branch for each possible outcome.
Whoa, wait. So the universe literally copies itself.
In this interpretation, yes. If a particle could be measured as spin up or spin down, when you measure it, the universe splits. In one universe branch, you measure spin up. In another, completely separate branch, an identical copy of you measures spin down. Both happen.
So infinite universes constantly branching off.
Potentially, yes. It sounds like science fiction, and the source acknowledges that. Critics often point to the, well, sheer extravagance of creating all these universes. It seems uneconomical, philosophically speaking.
A bit much, maybe.
Perhaps. But many worlds is a serious interpretation that comes directly from taking the quantum math literally. The source stresses there's no mysticism intended, it's just following the equations. And they argue it might be necessary if quantum mechanics applies universally.
And it's this many worlds idea that's crucial for quantum immortality.
It's the foundation. So let's bring it all together. How does many worlds lead to this idea of quantum immortality?
Okay, let's go back to the box. But instead of a cat, the source puts a person inside, facing, say, a gun linked to that 50-50 quantum decay detector.
Right, a sort of quantum Russian roulette, conceptually speaking. So the quantum event happens, decay or no decay. According to many worlds, what happens next?
The universe splits.
Into two branches. In branch one, let's say the decay happens, the gun fires, the person inside dies.
Okay, grim but clear.
Yes. But in the other branch, branch two, the decay doesn't happen, the gun doesn't fire. Or maybe, even if it does, some other incredibly unlikely quantum fluctuation occurs in that branch. The bullet spontaneously tunnels through the person, the gun mechanism jams in a unique way, something ensures survival.
So one branch death, one branch survival.
Exactly. Now here's the absolutely crucial mind-bending part, the core of quantum immortality as the source explains it.
Okay, I'm ready.
Think about it from the subjective perspective of the person inside the box. Which branch can their consciousness possibly experience?
Well, they can't experience the one when they die, right?
Right.
Because they're dead. Consciousness ends there.
Precisely. You only ever experience the timeline, the universe branch, where you continue to be conscious, where you survive.
So every time this life or death quantum split happens,
Your personal awareness, your subjective stream of consciousness always finds itself continuing in the branch where you lived. You can never, ever experience the branches where you died.
because you wouldn't be there to experience it.
Exactly. So from your own point of view, you seem to cheat death every single time. Your subjective experience is one of continuous survival against impossible odds.
Leading to the conclusion that, from my own perspective, I am immortal.
Subjectively immortal, yes, that's the core idea. Countless versions of you might perish in other branches of the multiverse, but the you that is experiencing this moment, your consciousness, will always inevitably find itself in a branch where it continues to exist.
Wow, that's a lot to take in.
It really is, and the source is very clear. This is a thought experiment derived from an interpretation of quantum mechanics. It's not practical advice. Don't go testing this.
Right, definitely don't try quantum Russian roulette at home.
Please don't. And from an outside observer's viewpoint, watching this experiment across the multiverse, they would see branches where the person dies. The immortality is purely from the inside looking out.
Okay, so let's circle back to that story from the beginning. The fall from the third floor, walking away. Okay, if we look at that through this many worlds lens.
Well, the implication is maybe in that instant the fall happened, the universe branched. In countless branches, perhaps, the outcome was tragic. The child died or was severely injured.
Okay.
But your consciousness, the one that continued, the one experiencing life right now and remembering that event as a near miss, is necessarily residing in one of the branches where, against the odds, you survived unharmed. That improbable survival was one of the quantum possibilities, and that's the branch your awareness followed.
It reframes those lucky escapes in a pretty profound way, doesn't it?
It really does. Though, again, the source stresses, this is one interpretation, science doesn't have a single final answer on this. Copenhagen, many worlds, other interpretations, they are all attempts to make sense of the incredibly weird but experimentally verified mathematics of quantum mechanics.
So it's okay to still be scratching your head a bit.
Absolutely. And the source encourages you, the listener, if this stuff fascinates you, definitely dig deeper. Read about the different interpretations, the ongoing debates. Don't just take our word for it.
Okay, so we've gone on quite a journey here.
Mm-hmm.
From Schrödinger's cat
Both alive and dead.
to the different scales of reality,
Oh.
the weirdness of superposition, how just looking changes things at the quantum level.
The observer effect, yeah.
And then diving into the interpretations, especially many worlds, leading us finally to this really wild concept of subjective quantum immortality.
It really stretches the mind, doesn't it? It shows how reality at its deepest level might be far stranger and more counterintuitive than we ever imagined.
Definitely. And it leaves us with a final thought, another analogy the source used that's kind of neat. It's about opening a door.
Ah, the balcony one.
Yeah, the Schrödinger's balcony idea. Imagine you're facing a closed door, and you genuinely don't know if the builder's finished putting a balcony on the other side yet.
Okay. Could be there, could be nothing.
Right. Until you open that door, until you interact, you observe maybe both possibilities exist in some potential sense. The moment you open it, your observation reveals one concrete reality for you. The balcony is either there or it's a long drop.
It makes you think, doesn't it? How many everyday interactions, even simple observations, are essentially collapsing possibilities, revealing just one path out of many potential realities? Something to ponder.